The t-distribution is very similar to the normal curve. Imagine that you have your normal curve right here. Now the t-distribution is actually a family of distributions, and the curves in this family are a little bit wider than the normal curve. And the reason is instead of having all of the data, or a lot of the data concentrated in the middle, a little bit less is in the middle and a little bit more is kind of out in these tails. So there's a higher chance of being out on the tails in the different forms of the t-distribution than there is with the standard normal curve, what sometimes called the z-distribution. Random historical fact, it was someone at the Guinness factory who worked in the quality control area making beer who realized that when he took smaller samples he would get more accurate data by using a different curve. And he wrote under the name student, which is why it's sometimes called student's t-distribution. Imagine you're faced with this problem. A student asked 20 seniors how many gallons of gas their car can hold. Sample average was 15.6 gallons with a sample standard deviation of 1.7 gallons. Find a 90% confidence interval. Now, whenever you see a sample standard deviation or something that doesn't imply it's the population standard deviation, you know that this value right here, this S, not sigma, is going to require a confidence interval based on the t-distribution. So our confidence interval is going to have the same basic form as we had before. Mu is equal to x bar, our best guess of the mean, and it's always going to be plus or minus our critical value, and that's going to be some value based on the t-distribution. We'll call that t star, and t star is going to be multiplied by our new standard deviation, our standard deviation based on the central limit theorem. That is going to be our sample standard deviation here divided by the square root of our sample size. So now applying that to this problem here, we see 20 seniors, and that is our sample size. So that's how many seniors we asked. N seniors, 20 seniors. We also have our sample standard deviation that we labeled over here, and we have an estimate of the mean, the 15.6, our best guess of the mean. So our confidence interval says that mu is equal to 15.6 plus or minus t star, which we need to find out in just a moment, times 1.7 over the square root of 20. Now this t star here, the way we get that, it's very similar to the way you'd get it with the normal curve, where you do inverse norm, except we do inverse t of all things. Makes sense, right? So if we have our t-distribution and we're finding a 90% confidence interval, that means that we have 10% left over. And 10% split between those two sides is going to be 5% per tail. So if I'm going to type in the function into my calculator to figure out where the t value is, kind of like a z-score, it's just a t-score, where that value is, what I'm going to do is I'm going to go to my calculator and go to the inverse t function. It's right by the inverse norm function in our distributions, and type 0.05. But unlike inverse norm, I have to add one more value. And this one's kind of tricky. You take your sample size and you subtract 1. So this 20 that we have up here is actually going to get subtracted by 1 to get 19. And that's what we're going to type into our inverse t function. So inverse t 0.05 comma 19. And when you plug that in, you get negative 1.73 if you round that off. And that is a t value, which is kind of like a z-score. And that's what we're going to plug in for our t-star. Since it's plus or minus, we don't really care about that minus sign out front, so we put in that 1.73 right here. And now we just have to clean up this part of the equation. The 1.73, our t-star, times 1.7 divided by the square root of 20. So we just plug that into our calculator. And we get 0.66. If we just round that off. So 0.66. So 15.6 plus or minus 0.66. And if you even rounded that off at 0.7, that would be fine. And that is equal to our population mean, which we call mu. Now when you're communicating problems like this in an AP problem, you're always going to need to share what your degrees of freedom, that is this 19 here, one less in the sample size, is called the degrees of freedom. You'll need to say what size confidence interval you're doing, what your t-star came out to be, and you'll always want to just write out this formula, because writing out the formula shows, one, you know the function, and two, you know what values need to go into it. So even though there are ways to actually do t-intervals directly in a TI-83 without doing any of this work, for clarity purposes, you're going to be better off just writing out the formula.